Have you ever wondered how an AI can learn to solve a really complex problem when it only has a few clues to go on? I mean, what if you had a literal mountain of information, but almost none of it was labeled? Well, today, we're going to unpack a brilliant solution to one of AI's biggest puzzles: how to learn from the unknown. So, let me set the scene. This quote comes from a researcher, we'll just call her Dr. Ada, and she was facing this classic machine learning dilemma. She had this massive data set of MRI scans, but only a tiny, tiny fraction were actually labeled by experts. The rest, just raw data, like a huge silent library. And to her, ignoring all that potential, well, it felt like throwing away treasure. So picture this. This is what she had to start with, just 100 MRI scans. Each one was painstakingly annotated by medical professionals to show, is there a tumor or not. This is that high-quality gold standard data. But it's a really, really small sample. And this is the treasure she was talking about. Over 10,000 other scans. Now, they contain incredibly valuable information, all these subtle patterns, but without any labels, a standard AI model has absolutely no idea what to do with them. And that's the challenge right at the heart of our story today. So this brings us to what we're calling the case of the missing labels. Dr. Ada needs to train a model to detect tumors, right? But she's caught between this tiny set of answers and this massive set of question marks. How in the world does she bridge that gap? Now, you're probably thinking, well, why not just label the other 10,000 scans? And the simple answer is, it's a huge bottleneck. Getting a medical expert to analyze and label even one MRI scan takes a lot of time and money. Trying to scale that up to thousands, it's often completely impractical for labs and companies. It's just not going to happen. But this is where a really clever approach comes into play. Instead of having to choose between the small labeled dataset and the huge unlabeled one, what if you could use both? This is the whole promise of a field called semi-supervised learning, or SSI. So the crucial idea here is that SSL is a kind of middle ground strategy. It's designed specifically for situations just like Dr. Ada's, where you've got a little bit of high-quality guidance and a whole lot of raw material to learn from. You really get the best of both worlds. Okay, here's a great way to think about it. Imagine a student. Those 100 labeled scans, they're like the solved examples in a textbook. They are absolutely essential for getting started. But the 10,000 unlabeled scans, that's like the entire rest of the library. By just absorbing all of that material, the student starts to learn the underlying structure and context, which makes them way smarter when they have to go back and solve new problems. Now, to pull this off, Dr. Ada needs a special kind of tool. Not just something that can recognize patterns, but something that can understand them so deeply that it can actually create new examples from scratch. And this brings us to the perfect tool for the job, the Variational Autoencoder, or VAE. So, what is a VAE? At its heart, it's a generative model. Its main goal isn't just to compress and then reconstruct an image. No, its real magic is in learning the fundamental essence of the data, its probability distribution, so it can generate totally new, realistic samples that have never existed before. And this difference is absolutely crucial. A standard autoencoder, that's what we see on the left, it's basically like a really good photocopier. It learns to copy an input as perfectly as it can. But a VAE, on the right, well, that's more like an artist. It doesn't just copy the images it sees. It learns the idea of the image, which allows it to create an endless variety of new works in that same style. Here's another way to put it. A regular autoencoder is like a photo album of cakes. A VAE is a cookbook. It learns the ingredients and the instructions, the recipe, so it can bake you a cake you've never, ever seen before, but one you'd instantly recognize as a cake. It learns the process, not just the final outcome. Okay, so we've got this powerful generative tool, the VAE. That's great, but how does this help Dr. Ada find tumors? Well, the answer is to build a kind of hybrid model, one that has two jobs at the exact same time, generating images and classifying them. Let's just walk through how this whole thing works, step by step. First up, an image goes into what's called the encoder. This part basically boils the image down to its core recipe, what we call the latent representation, or Z. Now, this little recipe, Z, gets sent to two different specialists. In step 3, the decoder uses it to try and rebuild the original image. But, and here's the clever part, at the exact same time, a classifier uses that very same recipe to predict the image's label, like tumor or no tumor. So how does this hybrid model learn? It's actually a two-part process. When it sees one of those 100 labeled images, it gets graded on two things: how well it reconstructs the image, and, of course, how accurately it guesses the correct label. But when it sees an unlabeled image, it can only really be graded on the reconstruction part. So it does something really clever. It makes its own best guess about the label, a pseudo-label, and it uses that guess to teach itself. By doing this thousands and thousands of times, the model uses all that unlabeled data to sharpen its understanding, which in turn makes the classifier way, way smarter. Okay, this all sounds great in theory, but does it actually work? Let's take a look at the payoff. Did Dr. Ada's strategy of combining all these ideas actually lead to a smarter AI that could learn from that mountain of unlabeled data? The proof is right here in the training logs. What we're looking at are the results after each full pass, or epoch, through the data. I want you to focus on that test accuracy number. See how it starts out low at just 17%, but as the model keeps learning from both the labeled and unlabeled scans, you can see it steadily climbing up and up. This chart just makes that progress crystal clear. I mean, look at that jump. The model went from a pretty dismal accuracy of 17% at the beginning, all the way up to 67% after just 20 epochs. That is a dramatic improvement, and it's all achieved by leveraging those thousands of unlabeled images that otherwise would have just been thrown away. And that right there is the ultimate takeaway. This VAE-based, semi-supervised approach lets us achieve significantly higher performance without the massive cost and time of labeling an entire dataset. At the end of the day, it's about working smarter, not harder. And listen, this isn't just some academic exercise. This same core technology is being used right now in really critical fields. It's helping to analyze medical scans, just like in our example. It's what helps self-driving cars identify objects on the road. It powers signature verification systems. And yeah, it even creates some of the realistic art and faces you see from generative AI. And it doesn't even stop there. The next level of this technology, something called conditional VAEs, gives us even more control. You can tell the model not just to create a new image, but to create one with specific attributes, like generate an MRI scan that has a tumor right in this specific region. The possibilities are just incredible. Which brings us to our final thought. The ability to learn from these vast, unlabeled worlds of data, it's a fundamental shift in how we build AI. It really is about finding treasure in the dark. So the real question is, if AI can learn this effectively from the unknown, what monumental puzzles is it going to help us solve next?